Okay, so we've been looking at sequences and special sequences, arithmetic sequences and geometric sequences. So an arithmetic sequence was where you had one term and you would add a term. You would add that term by a common difference called D, or D, the common difference. So a term plus D gave you the next term, and that common difference was always the same for an arithmetic sequence. For a geometric sequence, you're basically multiplying a term by some common ratio R to get the next term. And we were looking at examples. So here was an example. So show the, let me just pull it up. That's probably easier. Not show, determine whether no, that was not it. Here it is. Determine whether the given sequence is arithmetic, geometric, or either. So to determine if the sequence is arithmetic, so one way that we could tell that it was arithmetic is our common difference. We took a term minus the term right before it. It had to be equal to a constant. We couldn't have our variable left in there. So determine if the sequence is arithmetic, geometric. And we talked about it being geometric, our common ratio. If we looked at a term divided by the term right before it, if that gave us a constant, that's our common ratio, and it would be geometric, or neither. So if neither of these worked, then it wouldn't be geometric, arithmetic, or arithmetic. So for example, let's say you're given that your sequence, a sub n, is equal to 2n minus 5. And maybe this isn't an example, this is part A. Okay, so we're determining if this is arithmetic, geometric, or either. And so let's first, we're going to need it for each case. We know what a sub n is. Let's look at what a sub n minus 1 is. So we're going to go back in here, and wherever we see an n in our equation that gives us, our formula that gives us our nth term, we're going to plug in n minus 1. So this is going to equal the term 2. You see an n, we're going to replace it, so put parentheses, minus 5. Replace, or put in the parentheses, n minus 1. So let's reduce this a little bit by distributing our 2 inside the parentheses, so 2 times n, and 2 times negative 1, we get 2n minus 2 minus 5. Combining like terms, we get 2n, well, negative 2 minus 5 is negative 7. So we found what our a sub n minus 1 term is. We're given what our a sub n term is. So if it's arithmetic, so we're going to test to see if it's arithmetic. We want to first look at D equals the term minus the term right before it. Well, we can go back in and substitute this. So D is equal to the a sub n term, which we're given is 2n minus 5, minus the term right before it, which we just found to be 2n minus 7. We need that in parentheses, so it's minus that whole quantity. So we have 2n minus 5, distribute that negative, we get minus 2n plus 7. Combine like terms, 2n minus 2n cancels. -5 plus 7 gives us 2. So we get d is equal to a constant, and so this is an arithmetic sequence. Let's just say that we didn't know that, and we test to see if it was geometric. Let's see what happens there. So we want to test, we want to know if we look at a term and divide it by the term right before it, will we get back a constant? So looking at this, we get r is equal to a sub n, which we were given was 2n minus 5, all over a sub n minus 1, which we found to be 2n minus 7. Notice that this does not equal a constant. R is in terms of n. It's going to vary, and so this is not geometric. So since R is in terms of a constant, or is not in terms, it is not geometric. I already knew that because it was arithmetic, but I wanted you to go through and see what would happen if it wasn't geometric. And you put it in to figure out what R was. So part of the problem, or I don't think we were done, if the sequence is arithmetic, find the common difference. If it's geometric, find the common ratio. If the sequence is arithmetic or geometric, find the sum of the first 50 terms. Okay. Well, we found that it was arithmetic, and when we did that, we actually found what D is. D is our common difference. They wanted us to figure out in the example what the summation of the first 50 terms are. So we're going to look at when k is equal to 1 to 50, that summation of a sub n, but within terms of k. So you could write it as 2k minus 5. I'm just going to go through this and do it with, well, there's a couple ways we can do this. I'm going to give you the formulas. And so we can do it by using rules of our summations and break this down. Because really, this is the same thing, rules of summations. This is the same thing as 2 times the summation of k equals 1 to 50 times k, or of k, minus the summation of 5, k equals 1 to 50. We saw a rule that if you're looking at the summation of just the variable k, I gotta find it, sorry. This was equal to n times n plus 1 all over 2. And the constant, that one was equal to whatever this constant was, c times n. So let's write that out. So we have 2 times this piece in here. Well, our n value is 50. So we have 50 all times 50 plus 1, 51, all over 2 minus, now the summation of a constant, we're going to take our constant, which is 5, and we're going to multiply it times n. And n in our case is 50. So let's simplify that. 2's cancel. Well, 50 times 51. Well, let me just think about 5 times 51. 5 times 1 is 5. 5 times 5 is 25. So that's 255. Add a 0. So that's 2,550 minus, well, 5 times 50. That's 5 times 5 is 25 plus that 0 at the end. So I'm looking at 2,550 minus 250. That will give me 2,300. So without finding all 50 terms and adding them together, we could use a formula to do that. So this would be the sum of all 50 terms. But we also had a formula that said if our sequence is arithmetic, then we can use this formula. So if we had an arithmetic sequence, which we proved we did, let me find that. And again, these will be given to you, these formulas for the series. K is equal to 1 to n of a sub k. This is equal to n over 2 all times the quantity a sub 1 plus a sub n. Okay. This is only for arithmetic. So if we look at our formula, I'm just doing it a different way, showing it using this formula for arithmetic sequence, and we're going to show that we still get 2,300. And so if we look at our equation, let's go back and write it. So we have k equals 1. We're looking at from 2k minus 5, summing all the terms from k equals 1 to 50. So applying this formula, we have our 50 all over 2 times our first term and our last term. So we need to do a little bit of work on the side. We need to figure out actually what the first term is, and we can do that because we know what a sub k is. We go in here and we plug in 1 wherever we see a k, so we have 2 times 1 minus 5. So that's 2 minus 5, which gives us negative 3. So I need my a sub 1 term here, which is negative 3, plus my a sub n term. So my a sub n term, well, we're ending at 50, so n is 50. A sub 50, go back in wherever you see a k, plug in. So we have 2 times 50 minus 5. 2 times 50, that's 100. 100 minus 5 gives us 95. Plus 95 here. So let's simplify this. Order of operations, work inside the parentheses first. I can reduce 50 over 2, which is 25. And then negative 3 plus 25, that's 92. So multiplying out 25 and 92, we get back 2,300. Okay, so 2 different ways that we approach this using the summation and get the same result. So before we look at another one, let me give you the formula for geometric sequences or series. So if you have a geometric sequence, let's call it A sub n, then the summation from k equals 1 to n of A sub k, this is equal to the first term all times the quantity. We're going to have in the numerator 1 minus r raised to the nth all over 1 minus r. Have to have a couple different stipulations. Is there a question? I guess I just muted everybody. If you have a question, just pipe back in. So r can't be 0. Didn't make sense if our common ratio was 0. That was one of our stipulation. And in this case, r can't be 1 because that would give us 0 in the denominator. But here's a formula. Again, I told you I'd give you certain ones on the test, and here's one that I'll give you on the test. So this will be given on the final. Okay, you just need to know how to use it and figure out your values. So let's go back, and actually there might even be a more simplified form. No. So let's go back and look at another sequence. And I'm just trying to see which one I want to pull, but I don't know. Okay, let's just do this. Let's look at, you're given a sequence and you want to find out if it's arithmetic, geometric, or neither. Again, if it's arithmetic, you're going to find your common difference, D. If it's geometric, you're going to find your common ratio, R. If it's neither, well, then you don't have either of those. And then you want to find the first 50 terms of the sequence, if it's arithmetic or geometric. And you're given that the sequence is as follows. Sorry, my glasses. Let's say 3n divided by 2. So arithmetic. So if it's arithmetic, when we look at a sub n minus a sub n minus 1, this has to equal constant. Well, this is our a sub n value. We were given it. The nth term we would find by 3 raised to the n divided by 2 power. We can figure out what a sub n minus 1 is by plugging in n minus 1 wherever we see an n in the formula for the a sub n term. So this is 3 all raised to, you see an n there, rewrite it with n minus 1, all divided by, or that n minus 1 and the exponent is all divided by 2. So we're wondering, is d equal to 3 raised to the n divided by 2 power minus 3 raised to the n minus 1 divided by 2 power? Is this a constant? Can we manipulate this so that we do not have any more variables left on that right-hand side with n? I don't see how we can do that. So I could see that we could pull out some factors, But even if I pull out a factor, that's not going to rewrite it so that that expression 3 to the n over 2 minus 3 to the n minus 1 over 2 is a constant. And so the answer to that question is no. So is it arithmetic? No. Let's test to see if it's geometric. So if it's geometric, r would be a sub n divided by a sub n minus 1. We would get back a constant when we did that. And so if I look at my a sub n term, which was given, it's 3 raised to the n divided by 2 power, all divided by a sub n minus 1. Well, a sub n minus 1, that is the 3 raised to the n minus 1 over 2 power. So now we need to use rules of exponents. We have the same base, 3, and division, and so we can use the rule that we subtract the exponent, keep the base the same. So r is equal to 3 raised to the n over 2 power minus n minus 1 over 2. And that's all in the exponent of 3. It's kind of nice because we already have a common denominator. Well, let's make sure we distribute that negative, though, to both terms when we rewrite it as a single fraction. So we have r is equal to 3. And our exponent, well, n minus n, our n are going to cancel. And then we have a negative 1 times a negative 1. So that's going to just leave us with a positive 1 in our numerator. And we have our denominator of 2. So when we did this, we got back a constant. And so we know that this is a geometric sequence. This is a constant. So our sequence is geometric. So I can simplify this. I can leave this as r raised to the 1/2, but if I want to rewrite this as a radical, I can. The 1/2 power, this is the same thing as r equals square root of 3. Okay, so we found our common ratio. It also wanted us to find the sum of the first 50 terms. Okay, so we're looking at summation of k equals 1 to 50 of this 3k divided by 2 power. Our sequence is geometric. Let's see if I can pull this down. Oh, shoot. Okay. So let's use our formula. So for our formula, we need to know what our first term is, and we need to know what r is. Well, we found what r is, and actually I want to keep that as a radical, or as a exponent, 1/2 power. I'm noticing it's going to be easier to deal with when we're working with it. So we know what r is. That was cool. It's the square root of 3. We can figure out what our first term is. So our first term is a sub 1. So if we plug in 1, where we see a k, or go back up to our original function, a sub n equals 3 raised to the n over 2. So if I plug in 1, I get 3 raised to the 1/2 power. And I just told you I wanted to keep that with an exponent, and I wrote it with a radical. So r is the same thing as 3 to the 1/2 power. So I'm going to go over here and I'm going to plug in our values. So this is equal to our a sub 1 term, which is 3 raised to the 1/2 power, all times the quantity, one minus r, raised to the nth, our nth power is 50, all over 1 minus r. And our r, we said, was 3 to the 1/2 power. I guess it really depends on where you have it and how I would write it, but I'm just going to do it now since I said I was going to write it as 3 to the 1/2. So I'm going to move this for a minute. And so now we need to simplify this. So I'm now going to go rewrite this as the square root of 3, all times the quantity, 1 minus, well, exponents. Power to power is multiplication, so this is 3 raised to the 25th power, all over 1 minus the square root of 3. I'm not sure how much they're going to clean this up. We have the square root of 3 all times 1 minus, well, 3 to the 25th power is going to be a huge number. Yeah. Using scientific notation, it's 8.47 ... times 10 raised to the 11th power. So that's bringing that out 11 times. So we're gonna leave it in exact form, okay? So 1 minus 3 25ths all over 1 minus root 3. I'm not sure if they actually want you to rewrite that, getting rid of the radical. We can rationalize the denominator if we don't have to. I'm just gonna leave it in that form. So let me just pause and look in the back and see if that's what they did. Okay, so we do want to rationalize our denominator. They do keep it in the form 1 minus 3 to the 25th power because that's so huge. So to rationalize the denominator, we have 2 terms there, and so we want to multiply by the conjugate. Let's kind of, it doesn't matter. So multiplying by the conjugate of the denominator, so we're just changing the sign between our 2 terms. So it's going to be 1 plus square root of 3. We're multiplying by a fancy 1, so it's equivalent. And so our denominator, the whole reason we did this is because this is now a difference of squares. And so we could square our first term, 1 is 1, minus the square of our second term. Square root of 3 squared is 3. And then let's just kind of rewrite this a little bit. So this is square root of 3, 1 minus 3 to the 25th power, that's a quantity, and then the quantity 1 plus root 3. We can simplify a little bit. We have 1 minus 3, and so that's going to give us -2. And if we really wanted to, we could pull that negative out front, and so I am going to do that. I don't like the negative in the denominator. But it's equivalent. So we have a negative, the fraction root 3, all times the quantity 1 minus 3 raised to the 25th power, and that quantity 1 plus square root of 3. Okay, so sequences can be infinite, and so we can actually have infinite series, and sometimes they converge or they can diverge. What it means to converge is that means that it's going to go towards a number. it's going to equal some number. If it diverges, it's going to keep growing and it's never going to go towards some number. Think about it graphically when we have horizontal asymptotes and we graph something as x went to infinity, that was heading towards some number. So if in calculus, we would be saying it's converging to whatever that horizontal asymptote was. Here, we're going to look at a theorem that says the following. So we have a theorem. Convergence of an infinite geometric series. So convergence of an infinite series, infinite geometric series. So if the absolute value of R is less than 1, so if that common ratio, that absolute value is a number between 0 and 1, or if that value R is between -1 and 0, not including 1, the infinite geometric series which is written as a summation k equals 1 to infinity a sub 1 r raised to the k minus 1 power converges, and its sum is a sub 1 all over 1 minus r. Okay, this has a condition that this again has to be less than 1. It diverges if that does not hold. Then the geometric series diverges. So let's look at an example. Okay, so determine whether each infinite geometric series converges or diverges. If it converges, find its sum. So determine whether the infinite geometric series converges or diverges. If it converges, find the sum. So let's say you had 2 plus 4/3 plus 8/9 plus ... Well, first of all, it told me that this was, and that's a 9. It told me that this was a geometric sequence. Let's show maybe if, let's say if it didn't say that, can we show that that's geometric? And could we figure out what our a sub n value is? Well, if we kind of look at what's going on, and sometimes it's helpful if you have fractions in there and some of the terms aren't written as fractions, maybe writing it as a fraction. It's helpful to look at any patterns that's going on. So looking at the numerator, kind of splitting it up and breaking it down. So let's just look at the numerator, 2, 4, 8. So to me, that looks like some power of 2, 2 to the first, 2 squared, 2 cubed. So let's look at the denominator. I have 1, 3, 9. So again, that's looking like something that looks like 3 raised to some n power. And so now we can kind of manipulate it to look how we want it. So let's first look at, let's find a sub n and the sequence. 2 4/3, 8/9. Okay, remember sequence, those are just the terms listed with commas. Series is when you're adding the terms. So I just want to find the formula for the a sub n term. Okay, so if we look at this again, I know it's 2 raised to the nth power, and we might have to go back here and manipulate. And it looked like this was 3 raised to some power. And I know that something raised to the 0 power is 1. And so, and we start with our first term with n equals 1. So if I plug in 1 here now, that I would get 1 where I wanted to for my numerator. If I plug in 2, I get the 4, etc. The problem is when I plug in 1 into the denominator for n, 3 to the first power is 3, and I don't have 3 in my denominator there. So to fix that, I could put a -1 here. And so when I put in 1 for my first term, 1 minus 1 is 0, 3 to the 0 is 1. So we just figured out how to find the a sub n term. We can tell here that a sub 1 is equal to 2. It gave it that to us by listing out the summation. And then we want to find our r value. In our equation, we need to figure out what r is, and r is what? Let's first actually rewrite this a little bit. I want to convert this to look like this. Actually, we don't have to do that. We can figure out what r is. How can we figure out what r is? We know that r is equal to a sub n, and this will also prove to us that this is geometric. The a sub n term divided by the term right before a sub n minus 1. We have our a sub n term here. This is 2 to the n all over 3 to the n minus 1. All over, so now I'm going to go back in, and wherever I see an n, I'm going to put a parentheses for now, and then I'm going to rewrite n minus 1 inside the parentheses. So a sub n minus 1, I have 2, I see an n in that exponent, so I'm going to put parentheses on there. All divided by 3, I see an n in the exponent, so parentheses, and minus 1 in that parentheses, and minus 1 in that exponent. So wherever we put a parentheses, we're going to go rewrite it and plug in n minus 1. Now we need to show that we're going to get back a constant. So we need to clean this up. It's not as bad as it looks. So this is technically the same thing as our numerator, which was the fraction 2 to the n power all over 3 raised to the n minus 1 power. It's divided by this piece down here. When I write it, I'm going to clean it up. So this is 2 raised to the n minus 1 power all over, well, 3 raised to the, our exponent n minus 1 is really 3 to the n minus 2 power. Well, division of fractions, you take your first fraction and multiply it by the reciprocal of the second fraction. Order matters. We have 2 raised to the nth power all over 3 raised to the n minus 1 power times the reciprocal here, so 3 raised to the n minus 2 power all over 2 raised to the n minus 1 power. We can rewrite this as a single fraction. We can rewrite it so that we could actually use rules of exponents here. This is strictly multiplication, so we can do that. So basically I have a base 2, 2 raised to the nth in the numerator, 2 raised to the n minus 1 in the denominator. So we have 2 raised to the n minus the exponent in the denominator. Which is this n minus 1 here. So 2 minus this n minus 1. And then we also have, so right here, we have the 3. So we have a 3 raised to the n minus 2 in the numerator. So let's look at that. So times 3 raised to the n minus 2 in the numerator. But we have base 3 in the denominator. So we can subtract off the exponent of n minus 2. Sorry, n minus 1. Okay, so let's distribute the negative. We have to distribute the negative here in the exponent. Simplifying this down, we have, this is equal to 2 raised to the n minus n. Well, n minus n cancels, and the negative times the negative 1, so this is 2 to the first times 3 raised to the, so distributing the negative and combining like terms. So this is an n minus n cancels, and here we have a negative 2 minus times a negative 1. So this is plus 1. Negative 2 plus 1 is negative 1. We write it with positive exponents, we get back 2/3. Okay, r is equal to 2/3. A sub 1 is equal to 2. And now we can tell if it's converging or not converging. So it's a geometric sequence. And r is, the absolute value of r is less than 1. So r is equal to 2/3. The absolute value of r is less than 1. So that tells me by that theorem, so this converges. This meaning A sub n converges. Okay, but it doesn't tell me what it converges to yet. So if I look at the summation of k equals 1 to infinity, and I summed this all up, where my A sub n term we said was 2, but I'm going to rewrite it with k. So 2 to the k all over 3 to the k minus 1 power. This is equal to, let me go back up and grab the formula. Actually, I can just find it. You guys probably are still copying stuff down. So this is going to converge to a sub 1, all divided by 1 minus r. So this is going to converge to our first term. Well, just looking at the problem, the original problem, we know what the first term is. It's 2. If we didn't, we can plug in 1 in here. Okay, so it's 2, our first term, all over 1 minus r. And r we just found was 2/3. Let's clean this up a little bit. We have complex fraction. We can get rid of that by multiplying by a fancy one. And that fancy one will be our least common denominator of all the fractions within, which is only one fraction, so 3. So we get 2 times 3 is 6. Distribute that 3 to the 2 terms in the denominator. And we get 3 times 1, which is 3, minus, well, 3 times the 2/3, the 3 cancels, just leaving with a 2. So this will give us 6 all over 1, or 6. Okay, so if you found an infinite number of terms using that sequence, which would take you forever, and you summed them, which would take you forever, you would find that that was equal to 6. So it's kind of fascinating that you can sum something and it goes and an infinite number of times and it goes to a value. Okay, so that, well, we're not done yet because we haven't done any applications of these. So let's look at applications of sequences in series. And I want a new page. So I flagged some problems. So applications of sequences in series. Okay, so we have seats in an amphitheater. It's an outdoor amphitheater, it has 35 seats in the first row. Then it's given that 37 seats in the second row, 39 seats in the third row, and so on. There are 27 rows altogether. How many can the amphitheater sit? Okay, so again, we have an amphitheater. And we have 35 seats in row 1, 37 in row 2, 39 in row 3, ... And we know there are 27 rows. And we want to find the total number of seats. The amphitheater holds. Okay, so if you look at this, we are looking at a series because we want to look at the sum. We want to look at 35 plus 37 plus 39 plus ... to, I don't even know what that would hold in here. I can find that in a minute. So let's look and see and show that this is a particular type of sequence. So if I look at the sequence 35, 37, 39, what am I doing to get from one term to another? So notice to go from one term to another, you're summing 2. One term to another, you're summing 2. One term to another, you're summing 2. So because this is a common difference, or a constant, you're adding the same thing to get the same term, or get to the next term. We have our common difference is 2, and this is arithmetic. So common difference of 2. And this is an arithmetic sequence. So now we can look at a formula for summation for arithmetic sequence. Let's actually figure out, because these are things that you guys would have to be able to do on the test. So let's figure out what our a sub n term is. So let's find a sub n. Well, we're given that it's arithmetic. And so arithmetic sequence, there's different forms of ways that we can do this. One of them was in writing it in terms of the first term and with the common difference. This is equal to the first term plus the quantity n minus 1 times your common difference d. So a sub n is equal to our first term. Well, if you look at the sequence, we know our first row was 35 seats plus n minus 1 times d. Well, that common difference, we're adding 2 seats per row, so times 2. So a sub n, we can leave it like this or simplify it. I'm going to simplify for now. I'm going to distribute my 2 and combine like terms. So doing that, I get 35 plus 2 times n, so 2n, 2 times the negative 1, so minus 2. So a sub n, another way to write this is 35 minus 2, which is 33. So 33 plus 2n. So I'm summing. I'm starting with the first row of the stadium amphitheater seating, which is 1. We were told that they have 27 rows. And we can use the formula 33 plus 2n. And that would give us any row between 1 and 27. But we want to sum those. And so now we want to use our formula for arithmetic and series. So summing an arithmetic series, you would go and look at your notes or what I'm giving you. This was equal to n divided by 2, all times the first term a sub 1 plus the last term a sub n. Okay, so let's plug in our pieces. So this would equal our n value, well, 27 rows, so 27 divided by 2, all times the quantity of our first row. Our first row, well, 33 plus 2 times 1 is 35, which I better have back up here, which it is, plus the last row. So I can find out what the last row is. I need to figure out what a of 27 is. Well, we can figure out what any row is by our formula now, which we found. So this is 33 plus 2 times 27. So this is 33 plus 2 times 27, that's 54. So 33 plus 54, that would be 87. So that was just side work to add my last row of seating, so plus 87. So 27 halves, 35 plus 87. That gives us 122. So I have 27, all times 2 goes into 122. 61 times. So 27 times 61 gives us 1,647. We're talking about seats in the amphitheater. For some reason. It's kind of fun. Okay, that's like, should we do another one? So looking at another word problem. So a new piece of equipment cost a company $15,000. Each year, for tax purposes, the company depreciates the value by 15%. What value should the company give the equipment after 5 years? Okay, so we have equipment. Costs $15,000. It is depreciating. We're saying at 15% a year. What value should the company give the equipment after 5 years? Okay, so let's kind of look at this, and let's look at this as a sequence. So, and the cost of the equipment as terms. So when we first buy the equipment, or the company first buys the equipment, that cost was $15,000. It's depreciating 15% per year. Well, let's think about that. So if it's depreciating by 15%, there's a couple ways we can think about that. We can think of it as we have our original value, 15,000 minus 15% of that. So 0.15, which is representing decimal form of the percent, times the cost, 15,000 in our case. Or think of it this way, if we factor out a 15,000 from both of these terms, this is really the same thing as 15,000 all times the quantity 1 minus. We'd be left with a 0.15 here. 15,000 all times, well, 1 minus 0.15 gives you 0.85. So basically, every year, we're taking this amount of 15,000, or the term before, and we're multiplying this by 0.885, and that would give us a new amount. So the next time I would have to take my term before, that amount, 15,000 times 0.85, and multiply it again by 0.85. So notice that to get from one term to a next, we're taking the term before and we're multiplying it by 0.85. So this is a geometric sequence. Our first term of that geometric sequence is $15,000. Our R value of this sequence is 0.85. We could write this as, with a term, A sub n is equal to the first term, 15,000, R, which is 0.85, raised to the n minus 1 power. So let's just make sure that that was right. If I plug in 1, I may better get my first value is 15,000. Okay. So after 5 years, the thing is, I'm actually now questioning myself, because are we thinking of 15,000 as really our first term? The company depreciates the value by 15% each year. Well, let's look at it. And so we want to know, what should the company give the equipment after 5 years? So basically, this would tell me I would want to look at A sub 5. And so A sub 5, going back in and plugging in 5 or wherever we see an n in the formula we got, we have 15,000 all times 0.085 raised to the 5 minus 1 power, or 15,000 0.085. Oops. Add one too many zeros in here. Should be 0.85 raised to the 4th. So I'm going to take 0.85. You have to raise that to the exponent before you can do multiplication. So 0.85 to the 4th times my 15,000. Yeah. Uno momento, please. 1 minute, please. 15,000. Okay, so this is where I was a little off and I wasn't sure, and I'm like, let's just do it and see. So we're off by 1 year. So basically that first term, that 15,000, they're not gonna reduce that after. You understand? Basically, when you claim it that time, it's gonna be reduced by 15,000. And so our first term technically is this 15,000 times already the 0.85. So if you think of it that way, let me just go back here and write this. So that first term times that 0.85 into the negative 1 power. Notice these are the same base. And so when I multiply these, I can add my exponents. So adding my exponent of 1 plus the n minus 1 gives me just n. So this is equal to actually 15,000. A sub n. I'm going to get some more room. Is equal to, and that's not where I wanted to put that. Is 15,000 all times the 0.85. So we were adding our exponents, 1 plus n minus 1. So that just gave us the nth. So now when we look at a sub 5, so after 5 years, this is 15,000, 0.85, all raised to the 5th power. Which, if you do that, you get $6,655.58. Okay, so there was an example of a word problem. It wasn't of a series because we weren't summing terms. We were just finding what our sequence was, the a sub n term, and then we could answer information, knowing what type of sequence it was. Okay, so let's pause there. So we're starting to review for the final and go over material more that like the material we had covered from the last exam, since what we're going to see at the final. So the following question says, put the equation of the conic section in standard form and graph the equation. If it is an ellipse, find the center and the major and minor vertices. If the equation is a hyperbola, find the vertices of the transverse and conjugate axes. If the graph is hyperbola, graph the asymptotes. If it is a parabola, find the vertex, foci, and directrix. Okay, so we talked about looking at these equations and identifying what conic section it was. So first thing that you want to look at when you're looking at the equation is there both an x squared term and a y squared term? If so, then that rules out that it's not a parabola. If it just has one x squared or one y squared, then we know it's a parabola. If it's the x part that is squared, it's going to be up or down. If it was just the y part that's squared, it's going to be either left or right parabola. If you had both x squared and y squared and they were the exact same number, exact same coefficient in front of the x squared, y squared, then it was a circle. If they were not the exact number and they were the same sign though, both positive or both negative, it ended up being an ellipse. And if they were opposite signs, it was a hyperbola. So looking at the following, the equation 8x plus y squared plus 1 equals 2y minus 4. So just looking at this, I can verify what it is, and I can tell that this is going to be a parabola. And it's either going to be left, facing left, or facing right. Right now I can't tell quite yet. So for parabolas, we looked at different forms, and let's look at the form that this would be in. So this would be in the form of y minus k, quantity squared, is equal to for the times A times the quantity x minus h. So we want to group all of our y terms to one side of the equation, all of our x terms and constant on the other side of the equation. So let's do that. We can do that by subtracting 2y on both sides. And let's subtract 8x on both sides. And let's subtract 1 on both sides. So we have y squared minus 2y. I'm going to leave a spot here because this is where we're going to add something here to make this a perfect square, is equal to, well, we had subtracted 8x, so this is negative 8x, and we subtracted 1 on both sides, so this is negative 4 minus 1, which is minus 5. If we add something on the left-hand side of the equation, then we have to add it on the right, so it remains equivalent. And so now we need to figure out how we're going to make that left-hand side a perfect square. So we need to complete the square. Our coefficient in front of our y squared is 1, so it follows the rules that we can complete the square. We look at half the value of b, so negative 2 divided by 2 is negative 1. So the same number that you would add to itself to get negative 2 is negative 1. And this constant is that number multiplied by itself. So negative 1 times negative 1 is 1. So we're adding 1 on this left-hand side to make that a perfect square. We're going to add 1 on the right-hand side to also make that a perfect square. So rewriting this left-hand side, we have y minus 1 quantity squared is equal to negative 8 x minus 4. This is not quite in the form that we want it. We need this coefficient in front of the x to be 1, and so we need to factor that value, that coefficient, out of both of these terms on the right-hand side. So we still have y minus 1 quantity squared on the left-hand side is equal to, so we're pulling a negative 8 out. So if we pull a negative 8 out of the first term, we're just left with x. Pulling a negative out of a negative, so we're left with a plus. So you have to think to yourself, what can I multiply this by, negative 8 by, to get back negative 4? Well, if we multiply negative 8 by a half, that would give us back that term of negative 4. So now it is in the form that we can tell what the vertex is. So it's in the form of hk. H is always with the x value, opposite sign. So this is going to be negative 1/2. And k is always with the y value. And so in this case, it's 1. So negative 1/2, 1. So if we did that, that would be about right here. Our value over here, this is negative, and so I can tell right now that my parabola is going to be facing to the left. We need to figure out what P is. P is the value that will give us the foci and the directrix, focus. And I might have just said P because that's a variable that I've been using pretty much all my career right now. This textbook uses A. So we need to figure out what that A value is. We know that that coefficient in front of this parentheses, this negative 8, this negative 8 is equal to 4A. So we can figure out what A is by looking at that equation. So 4A equals negative 8. Divide both sides by 4. We get that A is equal to negative 2. well, I don't really need to box that. That's going to help me figure out where my focus is and where my directrix is. So we are going to go out 2 to the left and 2 to the right from our center or our vertex to find those values. So if I go, and I know it's always facing towards the foci, so I'm going to go this direction, 2. So foci. We talked about it affecting the vertex in which direction, and so the foci that's affecting my H value, it's going horizontally, and so my H value was -1/2, and then we're going to subtract 2 from that, and my K value of 1 stayed the same. And so this is going to be -4/2 minus 1/2 is -5/2, or -2.5, comma 1. Focus is a point. The directrix, though, is an equation of a line. The directrix, the focus, or the parabola is always going away from that line. And so if it is going left and right, your directrix is a vertical line, and so it's in the form of x equals. And we're going out to the right, adding 2, so x equals 2 plus whatever the x value of my vertex was, which was -1/2. So this would give me x equals 1.5 or 3/2. Okay, so I can find some other values that would help me a little bit more to graph this. I noticed that I'm never going to cross the y-axis. So if I plugged in x equals 0, I would get back a complex number, imaginary number. It's going to go this direction, and my y-axis is behind that. I can find my x-intercept by letting y equal 0. So let y equal 0 to find the y-intercept. Let's see if I can do this. Try one more time. I'm wondering if I can put it over here. Ah, that was from before. This kind of stuff doesn't happen on a whiteboard or a chalkboard. Okay, let's ignore that for now. We're trying to find our x-intercept. We're letting y equal 0. So let me do it up here. So let x equal 0. I'm sorry, our y equals 0 because we're trying to find the x-intercept. I'm going to go back to the original equation. We have 8x plus 0 squared plus 1 is equal to 2, I see y there, 0, so 2 times 0 is 0, minus 4. If I subtract 1 on both sides, I get 8x equals -5. Divide through by 8, we get x is equal to -5/8. Okay, so it's crossing about -5/8 about here. And so we get a graph. So any questions on that one? Okay, so the next one, looking at it, 16x squared plus 9y squared plus 64x minus 54y plus 1 equals 0. Let's see if I can do this. It won't do that. Okay, I thought maybe it would grab it. Looking at this, we can tell, or hopefully you can tell what type of construction it is. It has both x squared and y squared, so it's not a parabola. Look at the coefficients in front of the x squared term and the y squared term. So coefficient here is 16, positive, and positive 9. So they're not the same number, so it's not a circle. They're the same sign, so that flags me that this is an ellipse. So for ellipses, we need to put it in a certain form so that we can tell the shape, if it's elongated with the x-axis or if it's elongated towards the y-axis, the major axis. And so rewriting this, we want to rewrite it so we're grouping all the x terms together, all the y terms together, and the constant on the other side. We're trying to manipulate it, and again, we don't know which one yet, but it's going to be in some form of x minus h quantity squared all over something, plus y minus k quantity squared all over something equals 1, where one of them is either a squared and one of them is either b squared. But right now we don't know until we have this done. We know that a is always the bigger number underneath when we're talking about ellipses. So let's rewrite this. And so we have 16x squared plus 64x. I'm going to leave a space here. Actually, it doesn't matter right now because I have to rewrite it so that it has the coefficient is 1. Group the y terms. So 9y squared minus 54y, and get the constant on this other side, negative 1. I'm wanting more room. Sorry, just bear with me. And so we're going to complete the square on this piece. But in order to complete the square, that coefficient in front of the piece that we're in front of the square, that variable squared, has to be 1. And so we have to factor that coefficient out of the term. So for instance, 16x squared plus 64x, we have to factor out a 16 from both of those terms. So if I factor out a 16 from 16x squared, you're left with x squared. If I factor out a 16 from 64x, I get a plus 4x. We're going to add something in here that's going to make this a perfect square. So I'm going to put a blank here. I'm going to add something on the other side in a minute that's going to make that a perfect square. So let's do the same thing with our y terms. So looking at our y terms,
wasn't it 54, negative 54y, and not negative 5?
It might have gotten erased when I went through to pull here. Or maybe, yeah, it is. Let me rewrite that. Thank you. This is 54y equals 1. So here, this is 54y. That makes it a little easier when you're pulling out the 9. But it might not erase because this is so I'm squeezing in the 4. 54y. So pulling out a 9, positive 9, from just the y terms, we would get y squared minus, so 6 times 9 is 54, so minus 6y. And then we're going to add something in here to make this a perfect square. This is equal to negative 1 plus what we were adding. Well, we have to be careful, not quite what we were adding. And then we're going to add something here. We have to add something here. Okay, so looking at inside the parentheses, now it's in the form that we can complete the square. And so looking at inside the parentheses for the x terms, we're looking for the number, same number that we would add to give us 4. So 4 divided by 2 is 2. 2 plus 2 is 4. And so that same number multiplying would give us our c value. So 2 squared is 4. The problem is we didn't technically add 4 on this side of the equation. The 16 outside of this parentheses is affecting everything, every term inside the parentheses. And so technically we really added 16 times 4. So I'm going to actually put that there. So plus, really what we added on that side was 16 times 4. Plus, and so let's do the same thing. We want to complete the square on our y terms. And so we're going to look at our b value, that coefficient in front of y. We're going to divide it by 2. So negative 6 divided by 2 is negative 3. And check it, negative 3 plus negative 3 is negative 6. And that c value for that y term is negative 3 times negative 3, which is 9. But technically, we didn't just add 9 on this side. We added 9 times 9 on this side because of the 9 outside of the parentheses there. So we have 9 times 9 here. Okay, so now we can rewrite that as a perfect square. 16 all times, well, this is the same thing as x plus 2 quantity squared plus 9. We can rewrite y squared minus 6y plus 9 as a perfect square, y plus, or actually y minus 3. Quantity squared is equal to, so negative 1 plus 16 times 4 is 64, plus 9 times 9 is 81. So we need to figure out what that number is. So what is that? So that is negative 1 plus 61, or 64, that's 63. 63 plus 81, that's 144. We need to get this, it's not in the form. It needs to be set equal to 1. And so you have to divide both sides of your equation by that constant on the right-hand side if it's not 1 already, to make it 1. And so we can do that by dividing every single thing by 144. The left-hand side, so each term on the left-hand side or each grouping is divided by 144, which helps because we can't have a coefficient of 1 in the numerator with that x minus h, or quantity squared. So 9 actually goes into, or sorry, 16 actually goes into 144, and that's 9 times. So we can rewrite this as x plus 2 quantity squared all over 9 plus y minus 3 squared all over 9 goes in there 12 times equals 1. So our a value is the bigger value. A squared is equal to 12. So a is equal to the square root of 12, which is 2 root 3. B squared, when we're talking about ellipse, is the smaller value. B squared is 9, so B is 3. Our center, HK, H, so opposite sign, is -2. K, opposite sign, so 3. And so I'm just going to graph it here. So let's locate the center, -2, 3. And because the larger value was underneath the y, we said it was elongated towards this way. And so we're going to go up and down that value of a. So we're going to go up and down about 2 root 3. Let me just get that approximation. Which is about 3.5. So I'm going to go up and down about 3.5 from here. So my vertices on the major axis, which it wanted, that's affecting my y value. So I'm going up and down a for my y value. So my vertex is going to be at -2, and then it's going to be 3 plus or minus, I'm just going to leave it in this form, 2 root 3. So going down 3.5, about here.
How did you get 12?
12, because I needed to make this coefficient on the right-hand side 1. And so if you divide, is it not 12? Is it 16?
It's 16, yeah.
Okay, thank you. So 144 divided by 9. Well, that makes the number a lot prettier. So that's 16. Thank you. So that means, okay, good. It's still elongated that way, but that means that my a value is 4. So I should think of this times that I have problems with my pen and stuff. This is giving you guys a chance to catch up. Maybe, hopefully that's the positive behind it. Okay, so we have a squared is 16. I want a pen now. Which is 4. So a is 4. So instead we're going up and down 4 instead of 3.5. I'm just going to say that's it. And then we're going to get our minor axes, minor vertices. We're going to go left and right 3. So left and right 3, that's affecting the x value of your center. And so let's see, So here we're at -2. If we go to the right 3, that would give me when x is 1. And if I go from x equals -2 to the left 3, that would hit me at -5. Did I go right? Did I do that right? Left 3. It just doesn't seem like it's symmetrical, but it's all not to scale. And so we got this parabola, or not parabola, ellipse shape. It's a little better. I did not list my minor vertices yet. So the minor vertices, that was affecting our x value from our center. Our x value was -2, and we added and subtracted our b value, which was 3. Our y value stayed the same of -3. Back here, I fix it. This was ±4. So technically I could write those points, but you got the idea. So almost identical way to do this when you're doing the hyperbola. The next one is a hyperbola. So if you look at this, we are going to want to complete the square. I can tell that it's a hyperbola because I have an x squared term and a y squared term. And the signs in front of the x and the y terms are opposite signs. Oops. I don't know which one it's going to be. It's the a value, and a is not necessarily bigger for a hyperbola. The a value is underneath the grouping that is positive. And so there's a couple different ways that this can be, but our shapes can look like this, where the parabola shapes go away from each other, look left or right. And if that is the case, it's in the form of x minus h quantity squared all over a squared minus y minus k quantity squared all over b squared equals 1. If, when we rewrite it in this form, we see that it was actually the negative was in front of the x part of the thing, we would have y minus k quantity squared all over a squared minus x minus h quantity squared all over b squared equals 1. So we need to go through that, and we need to complete the square and get it in that form, and then we can tell which direction. So I'm going to actually skip that for now. If we have time, or if you guys want to go over that tomorrow, we can. But we have time to do other problems. And then just 1 second. Okay, so the internet is not going the best right now, but we'll try to continue to go on. So the next question is determine the equation of each conic section described below. So it's a parabola with a focus at 1, 2, and a vertex at 3, 2. So for these problems where it's a conic section and they give you information about that conic section, the best thing to do is to graph what they give you, because from there you can figure out, what direction your conic section is going and then which generic form of the equation you're going to use. And so it tells me it's a parabola, and it tells me my focus is at 1, 2, so I'm going to graph that. So here's my focus. I'm going to label it. And then I have a vertex at 3, 2. So I'm going to go out 3, 2, go over 3 and up 2. Okay, so knowing that my vertex of my parabola is always going towards the focus. So that tells me which type of equation I'm using. This is where if my parabola is going left or right, the y value is the part that is quantity squared. And so we're going to look at the form y minus k quantity squared is equal to 4a all times the quantity x minus h. So from here, we're given information. We're given where the center is, or not the center, the vertex. The vertex is at hk, and so just be careful. The k value is 2. And our h value is 3. So let's go back and plug in that piece. So we have y minus k. So y minus 2 quantity squared equals 4 times a. We'll come back to that in a second. I'm going to leave it blank. All times x minus h. So x minus 3 quantity squared. So we need to figure out what a is. That a value, well, it has to do with our focus or our directrix. From our vertex, that is the distance from the focus to that vertex. So this distance here, well, we were given that this was at 1, 2, and this vertex is at 3, 2. And so that distance in here is 2. So from here, we have the equation of the parabola with the given information. So it's y minus 2 quantity squared is equal to 8 all times x minus 3 quantity squared. Okay, so same thing. You're given a conic section, you're given information, you want to find the equation. So again, you're going to graph what you're given, and that's going to help you figure out which equation or generic form of that equation you're going to use. So we're given that it's an ellipse, and we have vertices are 3, -3, and 3, 3, and the minor axis length is 2. Okay, so if I graph this, I have a point at 3, -3, and 3, 3. Okay, and my minor axis length is 2. I need to figure out what the center is. I need to know, is this elongated with the x-axis or the y-axis? If I look at this, and I look at the length between my center is going to be the halfway point between these two vertices. I don't know if those, it didn't tell me if those were vertices on the major or minor axis. But I know the center is a halfway point between there. So I can see that my center is going to be at 3, 0. But I also know that my center, or my vertex, or I also know the length of my major axis is 2a. Major axis equals 2 times a. Let's look at this length here. So that's basically the distance from the center to either the major axis. I've already seen on the major axis. And this length right in here is 3. And this length right in here is 3. And so I can see in here that A is bigger for ellipse, then A has to equal 3. if A is 3, and that's the length, then my major axis is actually going to be 2 times 3, which is 6. And the length of my minor axis is 2. Well, if the length of the minor axis is 2, half of that distance is 1. So that means we're going to go left and right from the center, 1. And so if I go left and right from the center, 1. I can have my picture here. I don't really need the picture, but that was just kind of helping me. So I know my B value. I know 2B equals 2. So B is 1. I know it's elongated where the major axis is parallel to the y-axis. And so the standard form of my equation is going to be x minus h. So x minus my h value is 3. So x minus 3 quantity squared all over, I'm going to leave that blank for a second, plus y minus k. So y minus k, well, y minus 0. I don't need that really y minus 0 in there. I'll put it though. Is equal to, these are always over something, is always equal to 1. A is underneath the term that the major axis is parallel to. And so major axis is parallel with the y-axis, so A value is going to be underneath the y quantity squared term, and it's A squared underneath here, so this is 9 in the denominator. Your B value is 1, and it's going to be B squared underneath here, so I'm just going to put it over 1, even though 1 squared is 1. And so this would be the equation of our ellipse. Okay, so going to the next one. A hyperbola with vertices 2, 3, and 2, negative 3, and passes through the point 0, 5. Okay, so again, we're going to want to start plotting these, what we have. So we have vertices at 2, 3, and 2, negative 3. These are our vertices, and it passes through the point 0, 5. So 1, 2, 3, 4, 5. They're vertices, so it's going to be looking like this. So we have a hyperbola that goes up and down, and so we're going to have the it in the form. So if it's up and down, it's the y value that's positive, so it's going to be in the form of y minus k quantity squared all over a squared minus x minus h quantity squared all over b squared equals 1. HK, so that's the center. Center is going to be between these 2 points of my vertices. Well, if I went up, down, 3, you can see that my center here is going to be at 2, 0. Oops. That's not a length of 2, that's a length of 3. Okay, so we would use A to go up and down from our center. And so going up and down from our center is 3. And so I can see that my A is equal to 3. So A squared is equal to 9. It's the other value I don't know about is my B value. But I can use this bit of information right here to figure that out. It told me that I had a point at 0, 5. If I plug in those values, 0 for my x, 5 for my y, into what we have so far, the equation we would, and we plugged in a squared, we plugged in 9, then we would just have an equation left with b squared, and we can figure that out. Okay, so I'm just gonna move down here. Okay, so I'm gonna rewrite this. This is y minus k. K is 0, so y minus 0 quantity squared, so that's 0, that's y squared. All over a squared, which we said was 9, minus x minus h quantity squared. We can see that the x value, the center is 2, so x minus 2 quantity squared, all over b squared, we don't know that, equals 1. So I'm going to use this fact and the fact that 0, 5 is a point. So if I plug in x equals 0 and y equals 5, this has to come back a true statement. Or I need to be able to figure out what b is. And so plugging that in, we have 5 quantity squared all over 9. Minus x, which is 0, minus 2 quantity squared all over b squared equals 1. So I have 25 ninths minus negative 2 quantity squared is 4 over b squared equals 1. So let's look at this, and this is an equation. We have variables, it's a rational equation. We can clear the fractions by multiplying by our LCD. So we can clear the fractions by multiplying by 9b squared. So 9 would cancel there, and we would be left with 25b squared minus, so b squares cancel here, 9 times 4, so 36, is equal to 9b squared. If we subtract 25b squared on both sides, actually, how about let's subtract 9b squared on both sides and add 36, just so we don't have to deal with negatives. So 25b squared minus 9b squared, that's 16b squared, is equal to, add 36 to both sides, divide both sides by 16. So b squared is equal to 36 over 16. That's all we really needed. So if we go back in here, gosh, I ran out of room, but it's okay, paste. And I plug in what b squared is. We found b squared to be 36 over 16, which we probably should reduce. They both have 4 in common, so that would be 9/4. So let's go back over here and plug in 9/4. Here. Okay, so from that information, we were able to find the formula of the hyperbola with the vertices at 2, 3, 2, 5, or sorry, 2, -3, and a point at 0, 5. Okay, so the next one was writing a formula for a sequence. Let me see what that sequence is. So I'm just going to write that down, and I'm going to pull up a new page. So we have 1/3, -2/9, 4 7 27. Okay, so given the following sequence, you're trying to find the formula, and you were given that the sequence was 1/3, -2/9, 4 27, -8/81, ... And we want to find a sub n. Okay, so I'm looking at this. I'm looking at the numerator, seeing if I can see any patterns. Before I do that, I notice I have positive, negative, positive, negative, positive, negative. We talked about alternating signs, and we could get that in the form if we have -1 raised to the nth power. Sometimes we had to add 1 or subtract 1 here, depending on what we wanted to do. It didn't matter, to make sure that we got the correct sign when we had 1. So I want positive first. So when I plug in 1 for n, that would make this -1 raised to the first power, which is negative. So I need this to have a +1 in here, or like I said, it could have been -1. Because now if I plug in 1 here, 1 + 1 is 2. It's going to be an even number. That's going to make that positive. So now looking at this, I have 1, 2, 4, 8. Well, I know something raised to the 0 power is 1. And so looking back here, 2, 4, 8, that looks like a 2 to the nth power. This is a case where I might want to make this, I need 1 at the first, so let's make this 2 raised to the n-1 power. Because if I plug in 1 for my first term, that gives me 2 to the 0 power, which gives me 1, which I need. So now looking at the denominator, I have 3, 9, 27, 81. Those are 3 raised to the nth power. And when n is 1, that would give me a 3 starting there in the denominator, which I need. So we found what the nth term of our sequence was. So the next question, it gave you a system, a non-linear system, x squared plus 4x, x squared plus y squared minus 4x equals 0, 2x minus y plus 3 is equal to 0. So it said graph the system. And solve algebraically. Okay, so looking at this, you should be able to determine what these look like. Looking at x squared plus y squared minus 4x equals 0, I can tell that this is a circle because it has both an x squared and a y squared term, and that those coefficients in front are 1. It's not quite in the form. I don't know where it's centered at, but I know if I can regroup my x terms and my y terms together, get the constant on the other side, I can complete the square. So doing that, I had x squared minus 4x. What am I going to add to that to make that a perfect square? Well, if I add, well, negative 4 divided by 2 is negative 2. Square that term, negative 2 times negative 2 is 4. Plus y squared. There's no other y term there, so I'm just going to add the plus y squared, is equal to, there's no constant to move the other side. This is equal to 0, but we added 4 on the left-hand side, so we also have to add 4 on the right-hand side. This left-hand side is now a perfect square, so x squared minus 4x plus 4, that is x minus 2. Quantity squared equals, oops, not equals, plus y squared equals 4. So this is in a standard form of a circle where you can tell what the center is. The center is at 2, 0. This is equal to r squared. R squared is equal to 4, so that means my radius is 2. So we know what the equation looks like, or graph looks like for the first equation, which is center 2, 0. We can go up, down, left, and right, 2 from the center. Those will give us points on the graph. Of our circle. So looking at the next equation, we have 2x minus y plus 3 equals 0. I don't see any squares, and this looks like to me a linear equation, which it is. It's almost in the form of y equals mx plus b. If I can put it in that form, then things look nicer. So rewriting that in this form, we could just add y to both sides. So we get y is equal to 2x plus 3. So I can see that we have a y-intercept at 3, and our slope is at 2, or 2 over 1. So if I go down 2, I would go over 1 to the left. And if I went up 2, I'd go over 1 to the right. So according to how I have this graph, it looks like these will never intersect. So graphically, to me, I would say that there's no solution. Our solution is going to be the points where they intersect. Well, let's show that algebraically. What's going to happen when we solve this algebraically is that we're going to get solutions that are imaginary numbers. Okay, so when we're solving this algebraically, we have to determine which way we want to do this. Looking at this, we can use our substitution method. We figured out what y was for the second equation. We solved for y, right? So you have to go back into the other equation you didn't use, and we can replace y with what x is, 2x plus 3. So let's go back and rewrite the first equation using that substitution. So we have x squared plus, wherever we see a y, we're going to rewrite that with 2x plus 3. So put parentheses, that is quantity squared minus 4x equals 0. Replacing that y with a 2x plus 3. If we distribute out 2x plus 3 times 2x plus 3, we get 4x squared plus 6x plus 6x, which would give me a plus 12x. I'm just doing this and combining like terms at the same time, plus 9. We bring down my x squared and my minus 4x. So looking at this, we have a quadratic equations. We solve quadratic equations by keeping things on one side of the equation usually. And we try to factor it, or we can use the quadratic formula or complete the square. X squared plus 4x squared is 5x squared. Here we have plus 12x, 12x minus 4x. This is plus an 8x. And then my constant, I have a plus 9 equals 0. Because this is not intersecting, my guess is that I'm going to get imaginary numbers. So let's just go ahead, and I don't have a coefficient of 1 in front of here, so I'm just going to go ahead and use the quadratic formula. So x is equal to negative b, negative 8, plus or minus the square root of b squared, 8 squared in our case is 64, minus a, or 4 times a, which is 5, times c, which is 9, all over 2 times a, so 2 times 5. So 64 minus 4 times 5 is 20. 20 times 9, that's 180. So negative 8 plus or minus the square root of 64 minus 180 all over 10. That's less than 0 underneath our radical, so this is an imaginary number. So there's no place of intersection. Or there's no solution. Which supported our graph and what we had done. We didn't think that we had a solution there. Okay, so might have one more time for one more. Here was another system of equations. X minus 2y equals 1, y equals the square root of x minus 1. Can we do it? Let's see. Okay, so again, looking at it, you should be able to tell what the graph looks like or be able to tell really fast. X minus 2y equals 1 is a linear equation. We're going to put it in the form y equals mx plus b. And so I'm going to add 2y. That gives me 2y plus 1 equals x. Let's subtract 1. We get 2y equals x minus 1. If I divide by 2, I have to divide everything by 2. And so we get y equals 1/2 x minus 1/2. So I know what y-intercept is. It's negative 1/2. And I know what my slope is. It's positive 1/2. Okay, and so if I go up 1, I'm going to go over 2. Up 1 over 2. So if I went down 1, I would go over 2. Down 1 over 2. The other one, y equals the square root of x minus 1. Well, that looks almost like y equals the square root of x. This minus 1, and I know y equals square root of x. What that looks like, this is kind of like a half sideways parabola. This minus 1 is doing some shift. This is going to shift it though. It's with the x, so it shifts it horizontally, and it's opposite, so this shifts it to the right one. So instead of this point 0, 0, it's going to go over here, 1. And then it's going to look like this. So I'm not exactly sure where this is going to intersect, but I can tell that it's in the first quadrant. So now we can solve. Let's go back here and let's plug in for y. We know what y is because of this equation. And so if we do that, we get x minus 2 times y. So x minus 2, but y is square root of x minus 1. And our parentheses equals 1. Okay, so notice that this is a radical equation. So solving radical equations, we do this by isolating the radical. If there's more than one radical, then you do it one at a time. So I want to get the x term on the other side. I'm going to subtract x. I get negative 2 times the square root of x minus 1 is equal to 1 minus x. Let's square both sides of our equation. I'm going to ignore, I don't want to divide by that negative 2 just because I don't want to deal with a fraction. But if I square a multiple of things, I'm going to use my rules of exponents that says I can square my negative 2 and I can square the square root. And if I square the square root, that gets me the x minus 1 equals, so you guys need to FOIL out 1 minus x times 1 minus x. So you have 4 times the quantity x minus 1. This is equal to distributing 1 minus x times 1 minus x. So this is 1 times 1 minus x. This is, now distribute the negative x plus x squared. So let's combine like terms and let's distribute. So we have 4x minus 4, distributing the 4 on the left, equals x squared minus 2x plus 1. Quadratic equation set equal to 0, subtract 4x on both sides, add 4 to both sides. So we have x squared minus 6x plus 5 equals 0. So I notice this factors. There's 2 numbers that multiply to a positive 5 and adds to a negative 6. So that would be negative 1 and negative 5. So this would be at x equals 1 and at x equals 5. So x equals 1 right here at that point. It says about right here. This is not our point. We have to go back in, figure out what y is. When x is 1, and that's pretty fast. If you plug in 1 here, 1 minus 1 is 0. So y would be the square root of 0, which is 0. If x is equal to 5, plug it in here, square root of 5 minus 1. 5 minus 1 is 4, square root of 4 is 2, so our y value is 2. So that's going to happen at the value 5, 2. And I can clean that up and make it look like what we had. Okay, so that's as much of time that we have going over to some material for the final. So I need to stop the video.